Hey, welcome back everybody. Okay, so as promised, what we're going to do in this video is look at an example where we solve this 1D time-independent Schrodinger equation. Now, this is going to be an approximation to a real system, but what I want you guys to consider is an electron trapped in a very thin layer of material. So this is our example. So maybe there is this really thin layer of material, like a sandwich. So, and I know that's slanty, I'm sorry, but you can think of the electron as being trapped in this thin layer. Now, the width of this layer we'll call L. Okay, so this might be one type of material, and then on either side there's a different type of material. So this might be a conduction electron, one that can move very easily. And maybe this is some sort of thin conductor or semiconductor material trapped between two other semiconductor layers. Okay? All right, what we're going to do is we're going to treat this quantum mechanically, and we're going to describe the potential energy function of the electron the following way. We're going to say, look, because it's trapped in this layer, in fact, I want to check one thing before I go on. Okay, 0. I wanted to make sure when I label my x-axis where I start with the left side of this layer. It's going to be x equals 0. So here's what we're going to do. We're going to say that if I make a sketch of potential energy, okay, so what I'm going to do, I'm making a plot. This is the x-axis. This is my energy axis. Okay, so this is my energy. I'm going to say that the layer begins, this thin layer begins at 0 and ends at some value x equals L. Now, I'm going to say that inside this layer, the electron is free to move. So it can move as if it's a totally free particle. So I'm going to say that there is 0 potential energy. Ooh, in fact, watch this. I can make this, let's make it red. Okay, so I'm going to say that U is 0 right inside the layer. Okay, that's 0. And it is completely and utterly trapped in here. So what that means is the potential energy is going to shoot off to infinity at this edge and infinity at this edge. And I'll explain why that's the case. But what we're doing is we're saying that U of x is this very special function. It's 0 if the electron is in this layer, which we're assuming it is. So between 0 and L, x is between 0 and L, and it's infinity else. Now, the reason this will trap the particle is there is no way it can climb what we call this potential energy well. There's just no way it can do it. And I'm going to harken back to physics 1. So let me just let me doodle over here. If you recall in physics 1, mass on a spring, you might recall that the potential energy function, the potential energy that this object has, is 1/2 little k x squared. Oh my gosh, here's another k. This is the spring constant. Okay, so this is just a special discussion we're having over here. All right, look, if I plot the potential energy function versus x, that's a parabola with its vertex at 0. So you would get this. Okay, that's your U. Now, let's say you pull this object, let's say it's a horizontal spring, so you pull the object to the left. That's going to give it a certain initial potential energy. Let's say it's right here. And then you let go. What's going to happen? if there's no energy loss, this is going to go back and forth forever. So one way you can analyze this is you say, okay, right at the point of release, it has no kinetic energy, all potential energy. That sum of kinetic big K plus potential U is conserved. So you could draw a straight line like this and say this is my total energy. So as this particle's going back and forth, it's trapped between this point and this point, right? It can't get out of this energy well, so it's trapped back. It's trapped to go back and forth. Right? In fact, remember the difference between this horizontal energy line, this total energy line, and the U, the parabola, is going to be the kinetic. So for instance, if I look right here, this much energy is going to be kinetic energy. Okay? So you can analyze this using this so-called energy plot. Well, what we're going to do up here is something similar. What we're saying is if this electron cannot ever get out of this well, then the well's going to have to be infinitely deep, because let's say it picks up some kinetic energy and raises its energy to here. Well, it's still trapped inside the well. Well, what if it gets even more kinetic energy through some excitation? Well, then it's going to be here. But see, it's still trapped in the well. And to guarantee that it's trapped in the well, we make the energy, potential energy, go off to infinity. Now, this is an approximation. This is definitely an approximation, but the math is easier to solve. The differential equation is easier to solve if we assume that this goes off to infinity. Okay, so this will be an approximation to an actual electron trapped in a thin layer. Okay, and by thin, it's got to be on the order of the matter wavelength of the electron, maybe 100 times or so, up to 100 times. So we're talking, these electrons for typical speeds, as we saw in the example, their matter wavelength is on the order of angstroms. So we're typically talking about no more than a few hundred angstroms of width. Okay, but we can actually grow semiconductor materials even thinner than that. Atomic layers of a solid are on the order of 5 or so angstroms. So we can actually grow single atomic layers. And that's something we can engineer with. We can actually make quantum devices where we treat the electrons as waves, like quantum lasers, quantum well lasers, tunneling diodes. These are all engineered layers of semiconductors that are grown, and the analysis is for their operation is using the wave-like nature of the electron, quantum mechanics. Okay, anyway, how would this look if we go to solve this? And by the way, this example, this is sometimes known as the one-dimensional infinite square well. Okay, so it's a well-known, no pun intended, but it's a well-known potential to start with when you're first learning how to solve the time-independent Schrodinger equation. The one-dimensional square, because it has these 90-degree corners here, infinite square well. Okay, so what's what we do? We take the time-independent Schrodinger equation, right? So that looks like this, minus h bar squared over 2m. And again, you don't have to follow the complete derivation. You are responsible for the results, okay? Plus u of x times psi of x equals this eigenvalue energy psi, E times psi of x. Okay, all right, so look, we only have to worry about inside the well, because there's no way that the electron is going to make it outside the well. Okay, so, and inside the well, we take the potential energy to be 0, so this is gone inside the well. So our differential equation looks like this. Okay? Okay, interesting. Equals E times psi. All right? Now I can rearrange this to get into more sort of traditional differential equation form. I could write it like this. Plus 2me over h bar squared psi equals 0. Now this is just a collection of constants multiplying psi, right? Okay, so do we know the solutions to this? Well, you might recall from differential equations that if you have an equation of the form d squared y dx squared plus some constant, I'll just call it by, equals 0, right? That's going to be solved by a harmonic cosine or sine, because you have to take the derivative twice and get back to the original function. So this is going to be solved by either a sine or a cosine. And you might recall, from differential equations, that this is a second order differential equation and involves a second derivative. So we're actually guaranteed two unique solutions. The two solutions, one's going to be a sine and the other is going to be a cosine. Okay? So let's just let's try one of these, okay? Just to show that it's a solution. So let's try a sine. So I'm going to guess that my eigenfunction psi is some a times the sine of, I need a constant because I have to have an angular argument. So I'm going to use little k on purpose. Kx is going to give me an angle. So x has units of length, so k is going to have units of angle per length. In fact, that's going to be, as we'll see, the angular wave number for the matter wave. Okay, so that's going to be little k. But right now it's just a mathematical constant. All right, so guys, let's see if that works. Let's put it into that function, that differential equation. So what's the first derivative of psi with respect to x? Well, I think the sine will turn into a cosine, and then I'm going to pull out a k. Right, remember how to do that. Let's take the derivative again to form the second derivative. So cosine will turn into a minus sine. I'll put sine. I will pull out another k, so I'm going to get minus k squared a times sine of kx. Okay? All right, so let's put that into our equation. This is our equation right here right now, right? So that's going to give me minus k squared a times the sine of little kx plus 2me over h bar squared times a times the sine of kx equals 0. And we have to be able to solve this equation for any value of x. Well, the actual function sine of kx, that's going to divide out. The a's divide out. So what we're left with is we do in fact have a solution as long as k squared, this constant squared, is 2me over h bar squared. Okay? All right, now, what if we had tried a cosine? Right, so what if we had tried a cosine? I'll let you show that it also will be a solution. So if we had said, okay, let's try psi is some, I don't know, b cosine, right? Just to represent, it's another constant. Doesn't have to be equal to this a. B cosine kx. It would lead to the exact same condition. So in general, our two solutions, again, are the sine and the cosine. So any linear combination, I can add these together with any a and any b, and I'll still get a solution. Okay, so what do we do next? We have the general solution. Well, there's always, in physics, when you're looking at this actual physical system, there's always going to be what we call certain boundary conditions. And you guys probably did boundary condition problems in differential equations. And the boundary conditions we have for this particular system is we are assuming, remember, that the electron is trapped. So there is no way you're going to find it to the left of 0 or to the right of L. Now, this eigenfunction has to be continuous. That's one of the requirements of the total wave function. So that means we know that at x equals 0, this is going to have, this value of psi has to be 0. Because we know that psi is 0, you're never going to find the particle to the left of 0. Because it has to be continuous, it has to have the value of 0 at x equals 0. Similarly, the other boundary condition is that at x equal L, psi is 0. Okay? All right, so let's see what happens. Let's look at the cosine first. If we put in a 0 there, yes, we're going to get the cosine of 0. Well, that's 1. So how can we make psi equal to 0? Well, the only way we can get 0 is if this coefficient b is 0. Which means, physically, we don't even need this half of our solution. Right? Mathematically, it's a solution, but physically, it's not. So we don't need it. Okay, now, what about if we work just with the sine function? Well, we can definitely satisfy this condition, because if I put x equals 0 in there, the sine of 0 is 0, and we've got 0. Now we have to make sure we satisfy this condition, this boundary condition. So what that is going to lead to, let's put that boundary condition, let's apply that to our sine solution. So we're going to have a times the sine of this constant KL is equal to 0, right? Now, how can we satisfy that? Well, certainly we can satisfy it if a is 0, but then we don't have a solution because the coefficient is 0. So it has to be that the sine of KL is 0. So how can we satisfy that? Now, we could have, if we were mathematicians, we could have KL equaling 0. But then we don't have anything to work with because either K would be 0 or L would be 0, so that's not physically valid. I do want K and L to both be positive, okay? Because L is a length and I want my constant K to be positive. So we have to look for positive values of KL. Well, when will the sine of KL be 0? Well, I think if KL equals, let's see, pi. Yeah, pi. Can't have 0, but we can have pi. Oh, we could have 2 pi. Oh, we could have 3 pi, right? So let's write this as n pi, where n is going to be a positive integer. Okay? Hoo-hoo! So what we just found out is that by applying the boundary conditions, we get certain values for this k, quantized values for this constant k. But look up here. That k is going to determine the actual energies of the electron for the different energy levels, right? The different states, the different values of n. So we are quantizing the energies. Look, we have just found out that the energies of this electron can only have certain values, quantized energies. Okay, let's solve for it. E, right, up there, that circled equation, E is going to be h bar squared, little k squared, over 2m. But k can only have certain values, right? I'm going to put, in fact, we could write it like this. Look, k can only be n pi over L. So if we stick that in for our k, we could write this as E can be n squared, the integer n squared, times h bar squared pi squared over 2mL squared. We have just found out what the allowed energies are of the electron that is trapped in this layer if we approximate the potential energy as an infinite square well. It's a cool result because what it's saying is this electron that's bouncing around in this layer, going back and forth, can't have just any energy, only certain energies. So what's the lowest energy it can have? Well, that would be n equal 1, right? And E1 would be h bar squared pi squared over 2mL squared, whatever that turns out to be. M remembers the mass of the electron. This would be what we would call the ground state, analogous to, right, the hydrogen atom ground state. Then we could have, for n's that are greater than 1, E sub n is just going to be n squared times the ground state energy. So n equal 2, we could think of that as the first excited state, right? N equal 3 would be the second excited state, etc., etc. And see, mathematically it comes about because of the boundary conditions. Pretty cool. Now, in addition to knowing the energies, we also can solve and figure out what these actual eigenfunctions look like, right? Because remember, the functional form, and I'm going to put a little subscript n to emphasize that there are certain eigenfunctions for the different integer n's. Oh, and by the way, this n we would call the quantum number, this integer n, the quantum number. Okay, so this is going to be, I'll put a sub n, because there's going to be, right, each n will have a coefficient times the sine of k times x. But k, remember, is n pi over L, so we could write that these allowed wave functions or eigenfunctions are going to be n pi x over L, like that. Okay, now what do these look like? Ooh, here's where I'm going to go to the summary notes. Okay, let me show you guys. In this diagram that you see right here, oops, I'm sorry. What's sketched here, you see this orange potential energy well. What's sketched here for each level is what the eigenfunction would look like. So for instance, the ground state, n equal 1, if you plot that eigenfunction, which is a sine function, you'll get this. Whoop, that blue curve. See that? And remember, psi is going to be 0 at both ends, 0 and L. In the first excited state, you're going to get one more wiggle. It's going to look like this. Whoop, and you can verify this if you just plot your sine functions between 0 and L. Right in the middle, psi vanishes at 0. Psi 3, the second excited state, is going to look like this. Now, what's so cool about this is these look exactly like standing waves on a string. I mentioned standing waves on a string in an earlier video. So if you fix a string at both ends and you look for resonances where you get nice big antinodes, big displacements, you'll find these standing waves. This n equal 1 is called the fundamental, and then you get the higher harmonics. So the electron in this infinite square well approximation, it's acting just like a wave bouncing back and forth along a string fixed at both ends. And if you look at the wavelength, you can get the so-called standing wave condition. You see it right here. That is exactly what you would get if you analyze standing waves on a string. And in fact, I mentioned before, this k is the angular wave number. It is 2 pi over the wavelength of the electron. This is such a remarkable result that the electron has something, right, in common with standing waves on a string. And these resonances are determining the quantized energies. Okay? Now, you'll notice that the energies are not equally spaced for the infinite square well. In fact, the energy separations, right, they're getting larger and larger and larger. And the energy goes as n squared. Notice also that as L gets bigger, an interesting thing happens. If the width of this well, the width of the layer starts getting bigger, 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 all of these allowed energies get smaller, and the spacing between them also starts to decrease. And eventually what happens is that you can't even tell that you have discrete quantized energy levels. They're all just stacked right on top of one another, and that is a transition to the classical regime, classical physics, which says that an electron in a layer could have any kinetic energy that it wants, right? And so you see this transition from quantized physics, quantum mechanics, to classical physics, where any energy is allowed in these different physical systems as something changes. And in this case, it's as the well gets wider and wider. And another way to think about that is, is when the dimension of the well gets much larger than the wavelength of the electron. That's when you lose the quantum mechanics. That's when you can go back to classical particle physics. All right, so I know there's a lot going on here, and we're just, as you probably can tell, just starting to scratch the surface of quantum mechanics. But we're going to stop right here with this discussion. You are responsible for these results that you see in the summary notes, okay? So, but I wanted to show you what this would look like. Now, in a real system, let me just say two minutes worth. In a real system, if you were going to model an electron trapped in an actual layer, right, your potential energy function wouldn't be infinitely deep. So what it would look like, you still could approximate it as being square, but it would look something like this. If you were going to plot energy versus position x, it would look something like this. So the potential energy would be 0 here, then would come up, and then there'd be another constant value for that layer, and then this would come up, and there'd be another constant value for potential energy in that layer. That's called the finite square well. In that case, you can have the electron trapped. So maybe this is the ground state energy, right? And then here's another first excited state energy. But it may be that that's the only two bound energies that the electron can have. Because if it gets enough kinetic energy, it actually can escape the well. See, if it has enough kinetic energy so that its total energy is up here, it has leftover kinetic energy. It can actually escape and go into the other layers. The energies are not given by this expression right here in the finite square well model, this one right here. This is special. And the eigenfunctions are not given by that either, okay? But we won't look at that. Okay, so know the results for the infinite square well. All right, I'll see you in the next video where we'll talk about quantum mechanical tunneling, okay, which is a neat phenomenon. All right, bye-bye.